we calculated what is happening with flux if we put a shape or closed surface around a point charge. But now let's think about what happens if we have a point charge that's actually outside our surface. Now, this is part of why we needed to talk about inside versus outside, because it should be really clear, again, like a gerbil in a box versus a coffee cup, whether or not you're inside versus outside. So in this case here, we have some kind of curvy surface. You can imagine this as like a sock or something, but one that is completely closed. So not a very useful sock. And our point charge isn't on the inside, it's on the outside. So at some places, the field goes into the surface. And in other places, it comes out of the surface. So this is going to be more complicated to talk about. And one thing to think about is that, again, to do the math, we want to have a surface with some symmetry. So we're going to need to think about what that would look like. But the question we might ask is, what is the net flux? Which is basically our total flux is going to be, for instance, our flux in minus our flux out. But we would actually just calculate this all as our closed surface integral that you keep seeing. So we don't have to really calculate it as separate pieces, but that's one way to think about it, is you have some flux lines going in, some flux lines going out. So let's not actually do this kind of lumpy potato shape. Let's think about what type of closed surface we can do, where the point charge is outside of the surface. And remember that the key is you want to have your field lines to be either perpendicular to your surface or parallel to your surface. So if we imagine a side view, we want maybe the edges to be aligned radially with what our point is, and then we want these other surfaces to be circular with the centered on the point charge. So again, it's going to be a cross-sectional view. It's hard to think of a real-world object that would quite look like this, but we're basically doing like a pie slice almost, where someone has also cut out the center of it. That's a terrible explanation, but that's kind of what we're doing. And that is going to be something we can do the math over. So again, we're not choosing this because we must from a physics point of view. We're choosing this because we don't want to do hard/impossible math. So look, there's our simple shape. And we're going to have our radial pieces and our circular pieces. We then have negative flux and positive flux. So our positive flux is up here where your field and your A are parallel. So that's positive flux. Your negative flux is down here where they're antiparallel. So now here, what's our flux here? Our flux here is 0. What's our flux here? Our flux here is 0. So really, we just have to think about kind of this negative flux and this positive flux. But remember, what we have already said is that if you think about this kind of partial spherical surface and we change it to be slightly bigger, it's actually, the radius is going to cancel. And now, again, there's a mathematical way to prove this that I'm not going to go through, but notice that every field line that went in also comes out. Every field line that comes in comes out. And that wouldn't seem inherently to be true, but it actually would be true regardless of what shape we drew. So for this one, it's maybe the most trivial to see it, but it's actually going to be always true. So what that means is if the number of field lines intersecting your surface is the same when it's positive and negative, the magnitudes are equal, but you have two different signs, so your net flux is 0. This is a really important result. And again, there's a few conceptual ways to get here. Mathematically, you can set this up, though it's a little bit of a nightmare. You can also just try to think through the fact that every field line that goes in also comes out. And that's how you can see that your net flux is 0. So this is a really important general result. We haven't done a rigorous proof of it. In this class, we typically don't do the most rigorous proofs, but I've given you one example. So this is one concrete situation to think through, but it is actually generally true that if you have no net charge in your surface, so contain. So again, the inside of our surface was here, and there was no charge there. But in particular, the word net appears. So there could have been a positive and a negative charge there that canceled, but that makes everything harder. So again, it's actually true in terms of net charge, but we're not going to prove that. And the net electric flux is 0. So it doesn't depend on what your surface shape is. That kind of lumpy potato, it would have done the same thing. And so something to remember is that we do have individual pieces with flux. That's not saying the flux through every single bit is 0, right? There's negative flux there, there's positive flux there. But once you sum it up, the sum is 0. Now, this is part of why we must have a closed surface with an inside and an outside. Again, if we just said, hey, there's a surface and there's a point charge, maybe our point charge is inside, maybe it's outside. But again, here we have clearly an inside, and that just is not where our point charge is. And again, we haven't proved it, but this is fundamentally about the net charge enclosed. So if there's 0 charge enclosed completely, no positive, no negative, that's easy. But sometimes you're going to have a situation where there's 1 positive, 1 negative, and then your net flux is 0. One example of that would be a dipole. What would happen if we put a dipole in our surface? But right now we've started with a simple case, and I just am telling you in this case that it's actually a very general result.